Okay, welcome once again. We are going to continue with our topic on rectification, but today we are going to look at a single phase full wave bridge rectifier. I think that's the last part that was left under single phase rectification. Then we shall proceed to three phase. So bridge rectifier. So for the bridge, we shall see that it uses 4 diodes instead of 2 diodes compared to the center tapped full wave rectifier. So let us have the circuit diagram and also the waveforms. Then we look at the operation. Okay, so I will use my diagrams here just to explain the operation of a bridge rectifier. So what happens here, this is our waveform for the supply, then this is our circuit. So the principle of operation is that 2 diodes will conduct in one particular half cycle. Then when the waveform changes, then the other 2 diodes will conduct at the same time. For example, diode D1 and D4, the 2 parallel diodes, will be conducting during the positive half cycle of our input waveform. And the way they conduct, I've shown here in my diagram C using the red marker here. So during the positive half cycle, this point will be positive with respect to this point. So diode D1, so you can see diode D2 will be forward biased, and you can see I've shown that by using that continuous line to show that it will be conducting. So diode D2 will be conducting, then current through the load, then through diode D3, then back. And that's why I'm showing that the D1 and D4, they are not conducting, so they are open. Then the same, now when the waveform changes, that is at point T/2, half a period. So my point here now, this will be positive with respect to that point. So now diode D4 and diode D1 will be forward biased. That's why in diagram D you can see them shown shorted, while D2 and D3, since they will be reverse biased, we have shown them open from that diagram. So these are the output waveforms. So during the positive half cycle, the output will be that. During the negative half cycle, the output will be that. So you find that during both the positive and the negative half cycle, we shall have the output. And normally, we know that our output contains some ripples, so that's why we normally go for the average or the mean, which when we shall be calculating that will be around 0.636 as our VDC. So that is the principle of operation of a bridge rectifier. So as usual, we shall be getting the performance parameters. Performance parameters. So for the performance parameters, we start with the VDC. Performance parameters. So as usual, we start with our VDC, which is given by have 1 all over 2 pi. If we integrate the integral from 0 to pi Vm sine omega t d omega t plus the integral for the negative half cycle from pi to 2 pi and negative Vm, because it is the negative half cycle, sine omega t with respect to omega t. Yes. So from our integration, this will give us negative Vm all over 2 pi into cos omega t from 0 to pi plus Vm all over 2 pi into cos omega t from pi to 2 pi. So on simplifying these, you'll get Vm all over 2 pi times 4. And our VDC is 2Vm. It's 2Vm all over pi, which will give you our 0.636 Vm. So this is Vm, 0.636 Vm. So that is our VDC. So we can also get the root mean square voltage. So we have our VDC. We can also get the DC current that flows across the load. So we can also say that IDC will be equals to VDC all over 2 RF plus RL here. So our RF is the forward resistance of our diode. And why are we multiplying it by 2? Because there are 2 diodes conducting at the same time. So we multiply RF by 2, then we add the load resistance. So we have our VDC with us, which is now 2Vm all over pi into 2RF plus R. So on simplification, you will get 0.636 Vm all over 0, that is 2 RF plus R, which you can simplify as Vm divided by the total resistance will give you Im. So we can say 0.636 Im. Yeah. So maybe where our Im is Vm divided by 2 Rf plus R. So that gives you the root mean square current, the DC current. So the next parameter is the root mean square. So VDC, so root mean square. Voltage, that is our VRMS, is given by 1 all over 2 pi into integral from 0 to pi, so we square our voltage. So Vm squared sine squared omega t dt, so with respect to omega t, plus 1 all over 2 pi, the integral from pi to 2 pi, Vm squared, because here it was negative, so if we square negative Vm we get positive Vm, so Vm squared sine squared omega t with respect to omega t. So then we get the square root. We get the square root. So in the root mean square we square our voltage. So in simplifying this, you'll have maybe a step here. So we'll have Vm squared all over 2 pi the integral from 0 to pi then sine squared omega t can be written as a half into 1 minus, that is from your SMP tables, so a half into 1 minus cos 2 omega t d omega t plus Vm squared over 2 pi into the integral from pi to 2 pi, also sine squared from your SMP tables can be written as a half into 1 minus cos 2 omega t d omega t. So if we simplify this, this will be Vm squared all over 4 pi into, okay, let us not forget the square root here. This is under root. So we'll have Vm squared over 4 pi into, So if we do the integration with respect to omega t, 1 will give us omega t minus sine 2 omega t all over 2 from 0 to pi plus omega t minus sine 2 omega t all over 2 from pi to 2 pi. So getting the square root, this is simplified to Vm over root 2. Vm all over root 2, which is 0.707. 07 Vm. So that is our root mean square voltage, Vrms. So we can also get the root mean square current. Irms will be equals to Vrms divided by our total resistance, that is 2 Rf plus R. So which will give us Vm all over root 2 into 2 Rf plus R. On simplifying this, we get 0.707 Vm all over 2R F plus R. So which can also be written as 0.707 Im, where we said that our Im is Vm over 2Rf plus R. That is the root mean square current. Maybe the next parameter here can get the DC power, that's the output power across the load, PDC. PDC, the output DC power, which is given by, can use IDC squared times R. So we have our IDC, so it will be 4 Vm squared R all over pi squared into 2Rf plus R. This will give us our PDC, because IDC is here. You have it, Vm all over 2Rf plus 2R. So if you square that, then you multiply by R. So this expression will give you the PDC. Then we also need the input power. How the input power, Pin, which is given by Irms squared times the total resistance, 2Rf plus R. So this will be Vm squared So our IRMS, it's here. So if we square that, then we multiply by R. So VRMS, okay, VM squared all over 2 into 2 RF plus R. Then we also have the PAC. Which is I squared or IRMS squared times R. Now here the forward resistance is neglected because normally at high frequencies RF is normally negligible. Actually at AC the forward resistance of a diode is normally very small. So that's why PAC here we only consider resistance of the load. So which will give VM squared R all over 2 into 2RF plus R squared. So now we can get the rectifier efficiency. So therefore rectifier efficiency will be given by PDC all over P in. So you have your PDC, you have your P in. So this will give you around 0.812 all over 1 plus 2RF all over R. So for maximum efficiency, 2RF should be very small compared to R. So we can say for maximum efficiency, 2RF is very small compared to R. So therefore Nmax, that is maximum efficiency, will be 81.2%. So you can see how the efficiency has been improved in the bridge rectifier. So we can also get other performance parameters like the form factor. So form factor form factor, which we can denote as FF, is given by VDC over VRMS. So VRMS all over VDC will give us the form factor. So that is VM times R all over root 2 into 2RF plus R. On simplifying these, okay, we multiply by pi into 2 RF plus R all over 2 Vm times R. You'll find that this gives us 1.11 as the form factor. Then we also have the ripple factor. Ripple factor which is denoted by this symbol here, is given by the square root of form factor squared minus 1. Form factor squared minus 1. And we have our form factor as 1.11. If you square that, subtract 1, you will have 0.482 as the form factor. And maybe lastly, the peak inverse voltage, PIV. So for a bridge, for single phase bridge rectifier, the peak inverse voltage, PIV, will be equals to Vm. Will be equals to Vm. So these are the performance parameters for single phase bridge rectifiers. So that's all about it. Maybe we can look at the advantages of our bridge rectifier. Can just maybe name them. So advantages of bridge rectifier. Advantages of bridge rectifier. So the first one, we could see here that we haven't used a center tap transformer, so there was no need of a transformer. So we say that the need for a center tap transformer is eliminated. So need of center tapped transformer. Center tapped transformer is eliminated. Yes. And also, the second advantage is that the output is twice that of the center tapped circuit. So, the output is twice that of the center tapped transformer. So the output is twice that of the center tap transformer for the same secondary voltage. For the same secondary voltage. Same secondary voltage. That point is very important. So number 3, maybe the peak inverse voltage is 1/2 of the center tapped transformer. So the third advantage is that PIV is 1/2 of the center tapped transformer. So those are the advantages of the bridge rectifier. Maybe we can also look at the disadvantages. So disadvantages. So the first one, we could see that it uses 4 diodes. So 4 diodes are required instead of 2 diodes. So 4 diodes are required instead of 2 diodes as it is in biphase. That's a disadvantage. Then, as we say that, there are always 2 diodes conducting at a particular time. So we're told that now the 2 diodes will be in series when during a particular cycle. So therefore, the total voltage drop in the internal resistance of the rectifying unit and the losses are increased. So voltage drop in the internal resistance and the losses are increased. Yes, so those are the 2 main disadvantages, because we know that during a particular half cycle, 2 diodes are in series and they will be conducting at the same time, so that one increases voltage drop in the internal resistance. So the losses are increased. So those are the disadvantages of bridge rectifier so far. And that marks the end of single phase rectifiers. So I want us to proceed to 3 phase.